In this module, we will continue with our discussion on the approximate methods in quantum chemistry. As you already know, why we need approximate methods is because Schrödinger equation for an atom or a molecule which contains more than one electron cannot be solved exactly. That means, in principle, one can solve Schrödinger equation exactly only for hydrogen atom. So, for other multi-electron systems, how to solve Schrödinger equation? The major problem in the solution of electronic Schrödinger equation for these systems comes because of the presence of the inter-electronic repulsion terms. And this term creates problems in the solution. Therefore, in order to solve Schrödinger equation for a chemical system which is multi-electron, one uses approximate methods. There are mainly two types of approximate methods which one uses in quantum chemistry. One is perturbation method, about which we have already discussed. Today we will talk about the variation method, which is very commonly used in quantum chemistry. We will discuss what is this method, because variation method is ultimately based on variation theorem. We will define this theorem and then we will also give the proof of the variation theorem. Later on in the subsequent modules, we will see that while studying the electronic structure of molecules, variation method is very commonly used. As a matter of fact, the two theories of chemical bonding, namely molecular orbital theory and valence bond theory, which we all have studied, they basically come from the application of variation theorem to the electronic structure of molecules. Let's now first of all study about variation theorem. Suppose there is a quantum mechanical system for which Schrödinger equation cannot be exactly solved. The corresponding Schrödinger equation for this system is h cap psi n is equal to En psi n. Now, this Schrödinger equation cannot be exactly solved, and here the ground state wave function will be psi 0 and the corresponding energy will be E0. Now, since it cannot be solved, therefore, according to the variation theorem, suppose we guess the ground state wave function, or what we call as trial wave function, or as an approximate wave function, that is psi a. Now, psi a is guessed, and this guessing is based on many physical and chemical considerations, and this psi a is not equal to psi 0, which would have been the exact wave function. Then once we propose an approximate wave function psi a, then according to variation theorem, the corresponding energy, that means the approximate energy Ea, is given by the relation. In the numerator we have integral psi a star h cap psi a d tau divided by integral psi a star psi a d tau, and this approximate energy according to variation theorem is always greater than the exact energy E0. This will be equal to E0 only if the approximate wave function is the ground state wave function. But we are already assuming that this cannot be solved. Therefore, in this case, approximate wave function will always give energy greater than the corresponding exact energy. And this is the definition of the variation theorem. Now one can see that according to the variation theorem, approximate energy Ea will always be greater than or equal to E0. And one needs to remember here that the closer psi A is to psi 0, the closer EA will be to E0. So that's basically very, very important. So if suppose we have two trial wave functions and each one of gives the approximate energies, then that wave function which gives energy closer to the exact energy will be the better wave function than the other. Now we will discuss about the linear variation principle. This principle helps us in constructing the approximate wave function. Now suppose that we propose a wave function psi A, which is an approximate wave function. Then according to linear variation principle, this approximate wave function can be written as a linear combination of the set of the wave functions which would have been obtained by the exact solution of the Schrödinger equation. So this is how one can explain the linear variation principle. That means the trial wave function is expressed as a linear combination of a complete set of normalized and orthogonal eigenfunctions psi 1, psi 2, psi 3 and so on. So this is any guess function can be explained in this way. Now this linear variation principle can be used to give the proof of the variation theorem. So let's see how variation theorem can be proved through the use of this linear variation principle. As we have already discussed, the approximate wave function psi A is taken as a linear combination of orthonormal set of independent functions. That means psi A is equal to summation an psi n. Here an etc. these are the various coefficients. Now if we take the approximate wave function, then according to the variation theorem, the approximate energy EA is given by the integral summation an psi n star h cap, then we have summation an psi n d tau, and then in the denominator we have integral summation an psi n star summation an psi n d tau. That's basically what comes from variation theorem. And if we consider all variational coefficients to be real and assume psi n to be normalized, that means psi n star psi n integral d tau is equal to 1, then one can expand this above equation as you can see here, and one gets the corresponding approximate energy EA to be given by the relation EA is equal to integral summation an psi n star h cap summation an psi n d tau. Now since h cap psi n is equal to en psi n, that means had the equation been exactly solvable, then this would have been the condition. Then using this, our equation becomes EA is equal to summation an star an integral psi n star en psi n d tau is equal to, this ultimately comes to be equal to summation an star an en. So this is what we get from the variation theorem. Now if we subtract E0 from both sides, as you can see here, one gets EA minus E0 equals summation an star an, then En minus E0. Because we have already shown earlier that summation an star an over n is equal to 1. That's basically the condition, we have already shown it earlier. Therefore, from here we get En is greater than E0 or ultimately EA is greater than E0, and that's basically what variation theorem says. So what we have learned so far is what is variation theorem and how an approximate wave function is constructed using linear variation method, and we have given the proof of the variation theorem, which says that whenever any trial wave function is used, then the corresponding energy calculated using variation theorem will be greater than the corresponding exact energy. Now we will go into the further details and define what is secular determinant using variation theorem. We have already seen that a trial wave function depends linearly on the variational parameters like an, which we talked about earlier. Now suppose we take a trial function which has n is equal to 2 and a1, a2, psi1 and psi2 parameters, then the corresponding trial wave function psi a will be equal to a1 psi1 plus a2 psi2. We are limiting our trial wave function to only two functions. Here we are assuming that a1, a2, psi1 and psi2 are all real. Now using this as the trial wave function, one can get the corresponding approximate energy EA by the variation theorem as it is shown here. And if we substitute the values of psi A in this, one can see that this expands and ultimately we get, as you can see here, the numerator becomes A1 square H11 plus 2 times A1 A2 H12 plus A2 square H22. Then in the denominator we have A1 square S11 plus 2A1 A2 S12 plus A2 square S22. Here one must notice that H12 or H21, they will be equal. Why they will be equal? Because Hamiltonian, as we all know, is an Hermitian operator, and the definition of H12 is integral psi 1 h cap psi 2 d tau. So that's basically what H11 or H12 is. Similarly, we can define SII or SJJ corresponding to the integrals psi I d tau or psi j d tau, and the corresponding Sij would be integral psi I star psi j d tau. But if we are assuming them real, then there is no problem. We need not even use psi I star or psi j star. Now once we have got the expression for the approximate energy EA, now as you can see here, we can rearrange this equation and get the corresponding equation, which is EA multiplied by A1 square S11 plus 2A1 A2 S12 plus A2 square S22 is equal to A1 square H11 plus 2A1 A2 H12 plus A2 square H22. Now if we differentiate this equation with respect to A1 and then apply the condition for the minima, that means put the differential equal to 0, we get this equation, which is A1, then we have in parentheses H11 minus ES11 plus A2, in parentheses we have H12 minus ES12 equals 0. Similarly, if we had differentiated that above equation with respect to A2, we would have got another equation which would have been A1 into H12 minus ES12 plus A2 into H22 minus ES22 equals 0. So we get a pair of linear algebraic equations. We got two equations because we had chosen, while defining the trial wave function, only two wave functions, psi 1 and psi 2. And we had two coefficients, A1 and A2. Suppose we had chosen three wave functions, then we would have got three such equations. Now from these equations, one can see that this will give us a non-trivial solution only if the determinant of the coefficients is equal to 0. That means the determinant is H11 minus ES11, then H12 minus ES12. Then in the second row, we have H21 minus ES21 and H22 minus ES22. Here, please remember H12 will be equal to H21 because Hamiltonian is Hermitian, and also S12 will be S21 because they are ultimately the same things. So this determinant which we get here, this determinant is called secular determinant. The solution of this secular determinant will give us a second order secular equation, and then we can get the corresponding approximate energy. Extending this argument, if we had n functions, then in that case our determinant would have been of order n by n, and it would have been as it is shown here. The first row is from H11 minus ES11, it goes up to H1n minus ES1n. And then the last row would be, as you can see here, Hn1 minus ESn1, and it goes up to Hnn minus ESnn. And this secular determinant should be equal to 0. One can get the corresponding approximate energies. So this secular determinant, as you will see in the subsequent modules, is going to be of great importance. Whether we apply it to molecular orbital treatment or the valence bond treatment, while going through the electronic structure of molecules, everywhere we will have this secular determinant in some form. So in this module today, we have discussed about the variational method, and I've shown that this is an approximate method which is used in quantum mechanics. And then we also discuss that in the variation method, it is basically based on variation theorem, and according to this theorem, for any trial wave function, the energy which we get, that energy will always be greater than the corresponding exact energy. And how close that energy is to the exact energy will determine how good is the corresponding wave function which we have proposed. This variation theorem is going to be of great importance, and its uses we will study in our subsequent modules.